Alright, so I want to demonstrate how to make a Lewis structure given a molecular formula. Okay, this is a real big deal. It turns out that chemistry is a three-dimensional or four-dimensional topic, or I should say discipline. And so it's really important that we have the capability of thinking about the shapes and structures that we're dealing with when we do chemistry. So Lewis dot structures is a really big deal. Lewis dot structures. Okay? So in order to do this, I'm going to take a chemistry text, and I'll say that I would say any principles of chemistry text, any one at all, would have a set of rules about Lewis dot structures or Lewis structures in it. They may call it different things. It may simply be called Lewis structure, Lewis dot structure. I'm going to take one sort of arbitrarily. I'm just taking one off my shelf. And I'm going to go to the back of the text and find, I don't know if you can see this, this may be off camera. I'm going to find Lewis, there's Lewis theory, Lewis model, bond polarity, no, bond types, no, covalent bonding. Lewis model of covalent bonding is probably there, 332. Double bonds, 383. Electronegativity, formal ion. Of molecular compounds, 339. That's what I'm going to do. Lewis model of molecular compounds. Octet rule exceptions, you can see, are pretty close to the same thing, right? They're in the 340 range. So let's go to page 340. I don't know if you can see that on camera. Let's go to 340. And let's get the rules that we have there. Okay. So again, because of my tripod here, I may have a problem getting this on camera, but you can see, perhaps you can see on camera, if that's good enough. You can see Lewis structures. I know that's at a weird angle. You can't read that maybe. Lewis structures of molecular compounds and polyatomic ions. Okay? Writing Lewis structures for molecular compounds. And it starts out with rule number 1 here, and it goes on a little easier to see perhaps. Rule 2, 3, and 4. All right? You may have different rules if you're using a different text, but they're equivalent. I say different rules, it turns out they're going to be exactly the same thing. So what I'm going to do, because writing Lewis structures is so important, I'm going to make a 3x5 card and pull the same 3x5 card out for each problem that we do. Okay? Lewis dot structures. Step 1 is, I'm just going to read it to you because you can't see it. It is write the correct skeletal structure for the molecule. Okay. Wow. Correct? What's correct mean? Okay, we'll come back to that. Number 2, calculate total number of valence electrons. Okay. Step 3 is assign the electrons, bonds, or lone pairs. Okay. And then finally, the last rule is to move electrons either from bonds to lone pairs or lone pairs to bonds, double, triple bonds, etc., to satisfy octet rule. Okay, those are the 4 rules. We'll pull those out. Lewis dot structure rules. I'm going to put this on a 3x5 card, not because I expect to memorize it. I don't expect to memorize it. I just expect to do it over and over again until we use it. But I'm just going to put it here on a 3x5 card so I can pull this back out when we're doing problems later. Okay? So these are the 4 rules. of doing them. Now let me demonstrate them with this piece of paper here. I'm just going to put them right up here, out of sight for you. Okay, so we're almost always starting with molecular. I say almost always. I think we're always starting with a molecular formula. Okay, and then when we go from the molecular formula, we've got to do a Lewis dot structure in this question, and then later we're going to add more things. We're going to use this Lewis dot structures for tons of things. Okay, so there's a different flow. There's different paths that we can take after this point. All right, so let's take a molecular formula, a classic example of a molecular formula. Let's take water. Okay. Now, the first thing we're supposed to do is write the correct skeletal structure for the molecule. All right. So what does correct mean? And and I put that in parentheses here because that to me that's an open question, right? What does that mean? Well, the correct structure is a structure that works. Okay. And again, I'm guessing if you're just hearing this concept for the first time, that may bother you. But what we're going to do is we're going to make a guess. And correct skeletal structure means a structure that can give a valid Lewis dot structure. Okay? What does that mean? We're going to come to that. But for now, I'm going to give you something you can sink your teeth into. Default to symmetry. It's not always going to be a symmetric, but let's default to symmetry. All right? Let's put this off to the side. We'll come back to that. H2O. Step 1, write out the correct skeletal structure. I'm going to say default to symmetry. It's just a guess. Your first thing is a guess. So I'm going to say O, H, O, and H. Can you see how that's symmetric? Okay. Now the second one is calculate the total number of valence electrons. Well, there's two hydrogens, and each of those has one valence electron. That's one electron in its outer shell. And there's one oxygen, which has 6 electrons in its outer shell. Okay? So this gives us a total of 8 valence electrons. Alright, so we've done that. Step 2 is 8 valence electrons. Step 3, and I'm going to redraw this down here, okay? H, O, and H, just so we can sort of demarcate off which step is which. Assign the electrons. Alright? So we're going to go, I implied these two were next to each other. They were bonded, so I'm going to go ahead and put a bond between them. That's 2 electrons. And I've just changed that. I've got 6 left to assign. There's 2 more. I've got 4 left to assign. Okay? I'm going to put a lone pair here and a lone pair here. And so I've just assigned all of them. By the way, I literally do this. Each time I'm doing this, I will write out and I will count them because it's so easy to miscount. If you miscount electrons, this guarantees a wrong answer. Okay, you must not miscount electrons. So I myself am going to put extra care here with that. All right, and then the final thing is we move electrons to satisfy the octet rule. Okay, so before we move them though, let's go through here and see if the octet rule is satisfied for everything. Okay, I'm going to circle all the electrons around each. I'm just going to go left to right. Doesn't matter where you go. I go left to right usually because that way I can I have less to think about on game day. So, are there 8 electrons? Is the octet rule satisfied here for hydrogen? No, there's not 8 electrons, and there's only 2 inside that circle. However, hydrogen has only a capacity for 2 electrons in its outer shell. So, the rule should be called, is the outer shell filled, right? Usually the outer shell has got a capacity for 8 in the atoms that we're concerned about. But here that's got a capacity for 2, and it is satisfied. So I would say the octet rule is satisfied there, even though hydrogen is really an octet exception, but it definitely has its outer shell filled. Okay, now let's do oxygen 2, 4, 6, 8. It's satisfied. 2, that's hydrogen, so it's satisfied. Okay, we're good. So I don't need to move electrons. Step 4 was move electrons. Either move them from a bond to lone pairs, or lone pairs to a bond. And we have to consider double and triple bonds also, and we do this to satisfy the octet rule. Okay, so that is the octet, that is the Lewis dot structure for water.